Long before the modern investigations into the nature of the universe, before the intricate experiments of physicists and the sophisticated mathematical formulations of cosmologists, the question of whether the universe is deterministic, or if it even can be, was born in the quiet contemplation of ancient thinkers. This seed was planted deep in the fertile soil of early philosophy, where humanity first began to grapple with the profound mystery of existence itself. To truly understand the roots of the question, is the universe deterministic? We must journey back to the earliest civilizations, tracing the whispers of inquiry that emerged in the minds of those who sought to explain the nature of reality in a more ordered and systematic way than myth and legend could provide. This was the age of ancient philosophy, a time when the human spirit strove to find meaning through reason, observation, and argument. In many of the world's ancient cultures, stories of cosmic order and chaos coexisted with ideas about fate, destiny, and the will of gods. But as humanity matured intellectually, philosophers began to ask something deeper. Is the cosmos governed by necessity? Is every event predetermined by irrepressible causal chains? Or is there space within existence for chance, unpredictability, or freedom? Let us start with one of the earliest known glimpses of such thinking: ancient Mesopotamia. The civilizations of Sumer, Babylon, and Assyria cultivated extensive astronomical observations and sophisticated calendrical systems. Their priests and scholars believed the movements of celestial bodies held divine messages. But alongside religious interpretation, there was also a recognition of recurring patterns and causes. Although heavily intertwined with supernatural beliefs, these early efforts implicitly raised the idea that cosmic phenomena followed some regular, discoverable order, a principle that would lay groundwork for later deterministic thought. Meanwhile, in the vast expanse of the Indian subcontinent, ancient Hindu philosophy introduced profound reflections on the nature of reality and the self, reflected in texts known as the Vedas and later the Upanishads. Central to these traditions is the concept of artha, an underlying cosmic order or law that preserves harmony in the universe. This concept suggests a universe functioning according to fixed principles, which resonates with deterministic ideas. At the same time, these philosophies contemplate the interplay of fate, karma, and free will, hinting at complex tensions between predetermined outcomes and conscious agency. In ancient Egypt, cosmology was deeply infused with the cycles of nature: the flooding of the Nile, the rising and setting of the sun, and the eternal maintenance of Ma'at, the principle of truth, balance, and cosmic order. The Egyptians embraced a worldview that implicitly recognized the universe as orderly and predictable in its grand movements, governed by divine law. Through their myths and rituals, they sought to align human action with this cosmic order, again raising the question: if cosmic harmony is rule-based, does that mean every event fits inexorably within a predetermined cause-effect chain? But it was in ancient Greece that reflections about determinism found their earliest explicit philosophical formulations. The Greek world provided a rich intellectual environment where pre-Socratic philosophers began to speculate rigorously about the fundamental nature of reality, moving beyond mythological explanations toward naturalistic and rational inquiry. Heraclitus, famous for his statement that everything flows, panta rhei, emphasized constant change and becoming, yet he also believed in an underlying logos, an order and reason governing the cosmos. His philosophy suggests a tension between the flux of appearances and a deeper deterministic order beneath. This concept of logos could be interpreted as a cosmic rationality that guides all transformations with necessity. Contrasting Heraclitus, Parmenides argued for the unchanging, eternal nature of being. His radical view insisted that change and plurality are mere illusions. Reality is singular and fixed, a vision that can be seen as deterministic in the sense that reality simply is, without possibility for alternative outcomes. Empedocles and Anaxagoras introduced mechanistic models where cosmic phenomena arise from interactions of fundamental elements or principles, forces of attraction and repulsion, or nous, mind, intellect, organizing matter. Their work laid early foundations for causal explanations in nature, hinting at a universe governed by lawful processes rather than randomness or caprice. As these early philosophers wrestled with the nature of cause and effect, they set the stage for others who would more explicitly develop ideas about determinism. Most notably, the atomists, like Leucippus and Democritus, proposed that everything in the universe, matter, motion, change, could be explained entirely by the movement and interaction of tiny, indivisible particles called atoms, moving through the void. Their model introduced a profoundly mechanistic vision of the cosmos. Atoms followed precise laws of motion and combined in deterministic ways to produce all observed phenomena, including life and human thought. While the exact starting point of atomic motion was not always clear to them, the overall picture was strikingly deterministic. If one knew all atomic positions and motions at a given time, all future events could, in principle, be predicted. This conception resonated through the ages, influencing later thinkers and providing a conceptual bedrock for classical mechanics centuries later. Yet it also provoked significant questions. Did atoms move with complete necessity? Or was there room for chance to intervene? Early accounts differ, with some atomists like Epicurus later introducing the idea of a random atomic swerve to prevent strict determinism and allow for free will. The classical Greek thinkers also debated the role of the gods in causality. While some, like Aristotle, posited a prime mover that initiates motion without itself being moved, Aristotle's emphasis on teleology, purposes and ends as causes, added complexity to deterministic thinking by introducing final causes alongside efficient causes. Was the universe inexorably bound by mechanical chains of cause and effect? Or did purposeful design and goals also shape reality? The ancient philosophers' inquiries did more than philosophize. They laid the very groundwork for a conceptual framework to analyze causality, necessity, chance, and freedom. These discussions endured and evolved through Roman, Islamic, and medieval scholastic traditions, progressively shaping the intellectual climate from which modern scientific determinism would emerge. It is remarkable how threads from these ancient reflections remain alive in contemporary debates about determinism. The tension between a universe governed by immutable laws versus one open to randomness and freedom echoes through millennia, illustrating a profound human desire to understand not only how the cosmos operates, but what it means for our place within it. Thus, from the ancient philosophical roots, we find the birth of one of humanity's most enduring questions. Are we actors constrained by an unyielding cosmic script, or authors capable of improvisation amidst the universe's unfolding? This question, born in the minds of early philosophers gazing up at the stars and pondering change and permanence, still resonates deeply as we delve into the complexities of determinism and its many interpretations. As we move forward in this exploration, we will see how these ancient seeds blossomed into diverse philosophical and scientific doctrines, each wrestling with the question of whether the universe is, at its core, a deterministic machine or something more enigmatic. From Greek atomism to Enlightenment mechanics and onward to the quantum mysteries of today, the quest continues, inviting us to consider the profound mysteries about causality, chance, and necessity that lie at the heart of existence. Following the foundational reflections of the ancient philosophical roots concerning the nature of reality and causality, the story of determinism finds one of its most influential early expressions in the ideas of Greek atomism and the emergent mechanical philosophies. This chapter in our narrative marks a decisive turn as thinkers moved from broad cosmological speculation to the formulation of concrete models aimed at explaining the universe by means of fundamental entities obeying specific laws, thus setting the stage for a mechanistic and ultimately deterministic worldview. Greek atomism, primarily developed by Leucippus and his more well-documented successor Democritus around the 5th century BCE, proposed that everything in existence is composed of small indivisible units called atoms, from the Greek atomos, meaning uncuttable or indivisible. These atoms were thought to move eternally through the void, empty space, differing only slightly in shape, size, and position. The diverse forms and properties of the macroscopic world, ranging from inanimate objects to living beings, were explained by the arrangements and collisions of these atoms. This concept was revolutionary, as it sought to replace the belief in mystical or divine causation with the idea of natural explanations based on material constituents and their interactions. The mechanistic emphasis of atomism lay in its assertion that atomic motions and combinations follow consistent, necessary laws. If we imagine a universe in which all atoms move according to fixed, deterministic principles, then, in principle, the entire history of the cosmos and the behavior of everything within it become predictable, provided one had perfect knowledge of all atomic positions and velocities at any given moment. This seed of strict determinism was embedded in the very core of the atomistic worldview. Yet, the atomists recognized a subtle complexity. While they largely embraced a universe ruled by necessity and cause, Democritus and his followers also acknowledged the difficulty in fully grasping the reasons behind atomic motion. Some interpretations suggest that the initial motion of atoms could have a form of spontaneity, or at least was not fully explained in their system. This nuance introduces a faint early whisper of indeterminism, or randomness, a contrast that would echo through the history of the deterministic debate. In parallel with atomism, early mechanical philosophies made strides toward understanding the universe in terms of cause and effect relationships, stripping away supernatural intervention. Thinkers like Anaxagoras introduced the concept of nous, a cosmic ordering mind or intelligence that initiated motion and implanted an underlying order in otherwise chaotic matter. Although this notion invokes a rational purpose behind the cosmos, it still implies the universe operates within consistent causal laws, harmonizing with a mechanistic view. Aristotle contributed a powerful framework for causality that further influenced discussions on determinism, identifying 4 types of causes: material, formal, efficient, and final. His concept of efficient causes, which denotes the agent that brings something about, aligns closely with the notion of chain reactions and allows for temporal sequences governed by prior conditions. However, Aristotle's inclusion of final causes or purposes introduces a teleological dimension that complicates pure mechanical determinism by suggesting that certain natural processes aim toward ends, rather than merely resulting from prior motions. These early philosophies collectively paved the way for the more rigorously mechanistic and mathematically grounded frameworks that would emerge later, particularly during the scientific revolution. However, it is vital to appreciate them on their own terms, not merely as prologues, but as authentic and often nuanced perspectives that wrestled fundamentally with the questions of necessity, causality, and even freedom. Interestingly, Greek atomism was initially overshadowed by more teleological or essentialist philosophies dominant in antiquity. Yet it found more explicit advocacy during the Hellenistic period, especially in the works of Epicurus. Epicurus embraced atomism, but introduced the novel concept of the clinomen, an unpredictable swerve in the trajectories of atoms, to account for human free will and avoid fatalistic determinism. This tiny indeterminacy at the atomic scale represented an important philosophical attempt to reconcile a lawful cosmos with the apparent reality of choice and spontaneity. Parallel to these developments, Stoicism, another influential Hellenistic school of thought, mounted a contrasting vision with profound deterministic overtones. Stoics believed in a rational, providential, and interconnected cosmos governed by the logos, an intrinsic divine reason that ordered all things. They held that every event happens according to reason and necessity, emphasizing fatalism and cosmic determinism. Human freedom, from this perspective, arises from accepting the inevitable rational order rather than contradicting it. Thus, within ancient mechanical philosophies and Greek atomism, we encounter a rich landscape of ideas. On one hand, a universe conceived as an intricate, lawful mechanism whose every facet can be explained by the motions and collisions of invisible atoms. On the other, attempts to accommodate chance, spontaneity, or divine rationality alongside mechanism, concepts that would foreshadow enduring debates. The profound influence of Greek atomism reaches well beyond antiquity. Its mechanistic principles laid conceptual foundations for later scientific advances, particularly during the Enlightenment's embrace of Newtonian physics, which would articulate determinism with unparalleled precision. It also seeded fundamental philosophical challenges about the nature of chance, freedom, and causality, challenges that echo through the centuries. In contemplating this, we begin to understand how ideas about determinism were not born in isolation, but emerged from deep, layered dialogues about matter, motion, and necessity. They reflect the human endeavor to decipher an observed order in the cosmos and recognize the tension between predictability and spontaneity that defines our experience. As we transition forward in this exploration, we will see how the rich philosophical traditions of East and West grappled with similar themes of determinism and free will, unfolding a multifaceted dialogue across cultures and epochs. From the atomistic and mechanical philosophies of ancient Greece, the quest continued, awakening new ideas, challenging assumptions, and forever shaping our understanding of the universe's fundamental nature. As we broaden our perspective beyond the rich intellectual traditions of ancient Greece, it becomes clear that the question of determinism, the nature of causality, necessity, fate, and free will, resonates deeply across civilizations worldwide. From east to west, cultures have grappled with whether life's unfolding is governed by fixed laws or open to chance and choice, weaving diverse and complex philosophies around this enduring enigma. In the East, ancient Indian philosophy offers an intricate tapestry of doctrines reflecting upon determinism, freedom, and cosmic order. The concept of karma, central to Hinduism, Buddhism, and Jainism, envisions a moral causality. Every action generates consequences, inevitably shaping one's future experiences across lifetimes. This principle implies a deterministic universe in a moral or ethical dimension. Actions beget results with certainty, and the cycle of birth, death, and rebirth, samsara, progresses accordingly. However, Indian philosophical schools also emphasize the possibility of liberation, moksha or nirvana, suggesting a transcendence beyond deterministic cycles through wisdom and spiritual discipline. Within Hindu thought, the ancient texts known as the Upanishads and later Vedanta traditions grapple extensively with concepts of destiny and free will. while the universe functions under the immutable law of Urta, cosmic order. There remains room for individual self-realization and liberation, indicating a nuanced coexistence of determinism and freedom. Similarly, Buddhist philosophy critically interrogates the notion of a permanent self while underscoring dependent origination, pratyasamutpada, a chain of causation explaining the arising and ceasing of phenomena in a seemingly interwoven, law-bound reality. Yet Buddhism also emphasizes the potential to break free from suffering through enlightenment, pointing to an existential freedom amidst causal chains. Turning to Chinese philosophy, Confucianism, Taoism, and later developments offer insightful perspectives on determinism and harmony with the cosmos. Taoism, for instance, draws upon the Tao, the ineffable way or cosmic principle, as both the source and fabric of reality. The Tao is not a deterministic law in the rigid, mechanistic sense, but an organic, flowing pattern within which all things arise, change, and return. Practitioners seek to align with the Tao, embracing spontaneity and naturalness, Ziren, suggesting a worldview where deterministic order coexists with fluidity and freedom. Confucianism focuses on moral order, social harmony, and the cultivation of virtue. While it addresses duty, propriety, and destiny through concepts like Qianming, mandate of heaven, its deterministic implications are subtle and largely oriented toward ethical cause and effect within human society, rather than an all-encompassing cosmic determinism. In the rich philosophical legacy of the Islamic Golden Age, Islamic scholars absorbed, translated, and expanded upon Greek philosophical works, especially the works of Aristotle and Plato, refining the debate on determinism. The tension between divine omniscience and human free will emerged as a significant theological philosophical concern. Many Muslim philosophers, such as Al-Ghazali and Ibn Sina, Avicenna, wrestled with reconciling God's foreknowledge and omnipotence with the apparent freedom of human action. Some espoused occasionalism, the view that God is the only true cause and that what we perceive as causality is mere habit or divine intervention, thus lifting causation to divine determinism. Others leaned toward compatibilist views, where divine knowledge encompasses human freedom without constraining it. Within Western philosophy, as the classical antiquity period gave way to the Middle Ages, Christian scholasticism took center stage, inheriting the Aristotelian framework while interweaving it with theological imperatives. The medieval debate on determinism involved reconciling God's omniscience and providential plan with the reality of free will, a discourse exemplified by thinkers like St. Augustine and Thomas Aquinas. These discussions acknowledged a deterministic order in the universe as governed by God's will, but still affirmed human moral responsibility and choice, emphasizing a harmony rather than contradiction between determinism and freedom. The Renaissance and early modern periods saw the rise of mechanistic philosophies in the West, reviving and expanding atomistic and mechanical ideas. Here, deterministic perspectives often assumed a central role, but importantly, they did not arrive in philosophical isolation. Instead, they confronted long-standing religious, ethical, and metaphysical traditions concerning freedom, soul, and divine purpose. Throughout these world philosophies, a common thread emerges. The universe is perceived as governed by underlying principles or laws, whether conceived as cosmic order, divine will, natural causation, or moral law. Yet, alongside this recognition runs a persistent tension, a dialectic between necessity and freedom, fate and agency. For example, classical Stoicism from the West emphasized a deterministic cosmos ruled by logos, an all-encompassing divine reason. The Stoics saw human beings as parts of this great rational order, and while events unfold necessarily, virtue lies in accepting one's fate with tranquility. In contrast, Epicureanism posited the clinamen, or the swerve, an unpredictable deviation in atomic motion, introducing an element of indeterminism to preserve human freedom. In Eastern thought, such as in Buddhism and Taoism, the deterministic chain of causation exists, but is balanced by the possibilities of enlightenment or harmony, which transcend ordinary causal determinism, suggesting a multi-layered reality where different levels engage differently with notions of fate and freedom. This global philosophical mosaic attests to humanity's enduring engagement with determinism as both a metaphysical principle and an existential challenge. It teaches us that determinism is not a single idea, but a complex constellation of interpretations and tensions shaped by cultural, religious, and intellectual contexts. As we prepare to move into the Enlightenment era in our exploration, a period where these philosophical traditions converge with emerging science to crystallize determinism into a formidable scientific doctrine, it is worth appreciating how the centuries before it established a rich and dynamic foundation. The debates across East and West not only confronted the cosmos as a physical entity, but also wrestled with what determinism means for human life, morality, and freedom, thus preserving the profound mystery that still echoes in contemporary questions about the nature of the universe. Emerging from the rich tapestry of ancient and medieval philosophical discussions, the Enlightenment marked a profound turning point in humanity's understanding of the universe and its underlying principles. This era of intellectual awakening saw the rise of mechanistic thinking combined with rigorous empirical science, ultimately giving birth to a worldview where the universe was increasingly conceived as a vast, predictable machine governed by immutable laws. The Enlightenment's embrace of scientific method, combined with extraordinary advances in mathematics and physics, set the stage for classical mechanics to dominate our conception of reality and introduce one of the most compelling formulations of determinism in human history. At the heart of this transformation was Sir Isaac Newton, whose monumental works in the late 17th century synthesized and extended earlier discoveries into a coherent framework of motion and gravity. Newton's Philosophia Naturalis Principia Mathematica, commonly known as the Principia, presented a mathematical model of the universe operating strictly by laws of motion and universal gravitation. In this vision, every particle's behavior follows precise, predictable trajectories given its initial position, velocity, and the forces acting upon it. Newton's laws, elegant and concise, seemed to codify the cosmos as a clockwork mechanism. This mechanical universe, underpinned by Newtonian principles, was conceived as an immense automaton, vast, intricate, yet comprehensible and predictable. The paradigm suggested that if one knew all the forces and initial states of every particle, the future would unfold with perfect necessity. This mechanistic determinism reinforced earlier ideas from Greek atomism, but ramped them to unprecedented scientific rigor and applicability. Newton's achievements not only resolved many lingering questions about planetary motion and terrestrial mechanics, but fundamentally altered the human relationship with nature. No longer was the cosmos solely the realm of divine mystery or philosophic speculation. Instead, it became a vast system subject to discovery, measurement, and, crucially, prediction. The laws of nature were no longer considered arbitrary or capricious, but fixed and universal. This shift reverberated throughout the intellectual landscape. Thinkers began to envision the universe as a grand machine, one whose workings could be deciphered through careful observation, mathematical description, and rational deduction. Philosophers and scientists such as René Descartes had already proposed mechanistic models of physical phenomena earlier in the 17th century, emphasizing the role of matter in motion and rejecting Aristotelian notions of purpose-driven causes. Descartes imagined the universe as composed of matter in extension, moving causally without intrinsic purpose, laying conceptual groundwork upon which Newton would build. Moreover, the Enlightenment's mechanistic outlook came to permeate not only the natural sciences, but also metaphysics, ethics, and politics. The predictable nature of physical phenomena suggested a rational order underpinning existence. This inspired confidence in reason, encouraging the belief that even complex phenomena, including human affairs, might be understood, systematized, and influenced according to lawful principles. However, the deterministic vision did not face unanimous acceptance. Some scholars recognized the immense complexity and the practical limits of measurement, even if conceivably reducible in theory. Philosophers like Leibniz, a contemporary of Newton, acknowledged the deductive power of mechanistic laws, but emphasized the role of mind and metaphysical principles. Leibniz's concept of pre-established harmony proposed that the universe operates according to a divinely coordinated plan where substances, monads, unfold without direct causal interactions, a subtle departure from strict mechanical causation. Despite such nuances, the mechanistic worldview prevailed in scientific circles, guiding centuries of research and discovery. The universe's clockwork image became a dominant metaphor, reflecting the belief that natural events were strictly determined by prior states, describable by mathematical laws. This understanding profoundly influenced the Enlightenment's scientific revolution and shaped emerging fields like astronomy, thermodynamics, and later electromagnetism. Furthermore, mechanistic principles fueled advances in engineering and technology, providing practical proof of the predictable laws governing physical behavior. The steam engine, the expansion of industrial machinery, and innovations in navigation and surveying all attested to the utility and accuracy of deterministic models. These successes reinforced a worldview where certainty and predictability were not only metaphysical ideals, but tangible realities. It is essential, however, to appreciate that the Enlightenment's determinism was largely a classical idealization. While offering compelling theoretical clarity, it did not yet account for phenomena that would later challenge predictability, such as the behavior of gases leading to thermodynamics, or the chaotic complexity of certain mechanical systems discovered much later. Still, the classical mechanical model provided a remarkably successful framework, forming the backbone of what would be called classical physics. Newton himself maintained a nuanced position. He allowed that God played a role as the initial creator and sustainer of the universe, sometimes intervening to maintain order. This revealed the lingering presence of theological considerations even within the mechanistic paradigm, reflecting the ongoing tension between deterministic natural laws and metaphysical or religious perspectives. In the realm of philosophy, the mechanistic determinism inspired debates about human freedom and moral responsibility. If physical events are governed inexorably by prior causes and laws, what room remains for free will? Various responses emerged, ranging from compatibility efforts, arguing that determinism and free agency could coexist, to fatalistic perspectives that downplayed human freedom. As we prepare to delve into more explicit formulations of determinism, such as the concept famously articulated by Pierre-Simon Laplace, it is important to recognize the profound impact of the Enlightenment's machinery metaphor. The vision of the universe as an elegant, lawful system set the cognitive stage for later scientific advancements and philosophical reflections that would cement determinism's role at the core of modern physics, at least until the challenges posed by the advent of statistical mechanics and quantum theory. Thus, the Enlightenment era stands as a landmark in humanity's quest to understand the universe's deepest workings. Its fusion of empirical science, mathematics, and rational philosophy crafted a compelling deterministic framework. This framework, built upon Newtonian mechanics and mechanistic principles, enthralled generations and continues to influence scientific and philosophical thought to this day, even as we confront new complexities in later chapters of this journey. Building on the grand mechanical universe crafted during the Enlightenment, a realm envisioned as a vast clockwork governed by immutable laws and precise initial conditions, one of the most compelling and enduring notions of determinism was articulated by the French mathematician and astronomer Pierre-Simon Laplace in the early 19th century. This idea, poetically encapsulated as Laplace's demon, represents the epitome of absolute predictability. A hypothetical being who, armed with complete knowledge of the universe's state at one instant, could foresee all past and future events with perfect certainty. This concept not only crystallizes the deterministic ideal, but also invigorates philosophical debates that resonate to this day. Laplace himself was a towering figure of post-Enlightenment science, contributing foundational advances in celestial mechanics, probability, and mathematical physics. His formulation of determinism is rooted in the Newtonian universe framework, where all physical phenomena unfold according to laws of motion and gravitation, and every effect has a cause. Laplace imagined a being possessing, at any given moment, absolute knowledge of the precise position and momentum of every atom or particle in the universe. With such omniscience, given the laws governing their interactions, the demon could compute the entire past and future history of the cosmos, much like running a sophisticated computational simulation. This thought experiment elegantly conveys the logic and implications of classical determinism. It suggests that the universe is a colossal deterministic machine. Once all variables are known, nothing remains uncertain or open-ended. The future is, in principle, as fixed as the past, denying genuine randomness or contingency. Human actions, choices, and even thoughts, according to this vision, are simply outcomes of this unbroken chain of cause and effect. Consider Laplace's own words, which beautifully express this deterministic vision. An intellect which at a certain moment would know all forces that set nature in motion and all positions of all items of which nature is composed, if this intellect were vast enough to submit these data to analysis, would embrace in a single formula the movements of the greatest bodies of the universe and the lightest atom. For such an intellect, nothing would be uncertain, and the future, just like the past, would be present before its eyes. This passage not only captures the imagination, but also lays bare the philosophical stakes. While purely hypothetical, Laplace's demon has become a powerful symbol in both scientific and philosophical discourse. It embodies the naturalistic aspiration to know the universe in its entirety, to reduce all phenomena to mechanical law and initial conditions. It is a compelling vision of knowledge as omnipotent calculation, where uncertainty vanishes before perfect insight. Yet, the thought experiment invites profound questions and challenges. Does such perfect knowledge truly exist, even in theory? Is the universe truly deterministic in the strict classical sense, or do limitations, epistemic, practical, or metaphysical, undermine the demon's omniscience? Moreover, what are the implications for human freedom and moral responsibility if our lives are the inevitable unfolding of a cosmic machine? At a practical level, even if the universe obeys deterministic laws, the complexity and sheer scale of the cosmos makes the demon's knowledge and computation impossible for any finite intelligence. This raised early awareness of what today we call computational irreducibility. the idea that some systems, while deterministic, are too complex to be predicted in practice. Hence, determinism does not necessarily imply predictability for real-world observers. Laplace's deterministic ideal is also limited by subsequent scientific discoveries that complicate or challenge its assumptions. The emergence of thermodynamics introduced randomness and probabilistic descriptions of microscopic behavior. Later, chaos theory revealed that deterministic systems can exhibit extreme sensitivity to initial conditions, making long-term prediction practically impossible. Most strikingly, the development of quantum mechanics shattered the classical assumption of strict determinism, replacing it with intrinsic probabilistic nature at fundamental levels. Philosophically, Laplace's demon confronts us with the tension between metaphysical determinism and human experience of freedom and contingency. If all must unfold inevitably, what becomes of choice, responsibility, creativity? This problem spawned influential debates in compatibilist and incompatibilist philosophy of free will, many of which persist to this day. The influence of Laplace's demon endures not only as a foundational concept in debates about the nature of reality, causality, and knowledge, but also as a rich metaphor illustrating the limits and aspirations of scientific understanding. It provokes us to reflect on the meaning of prediction, explanation, and control within a universe that may be at once lawful yet resistant to complete grasp. In our ongoing exploration, the demon's vision offers a powerful vantage point to appreciate both the power and the limits of classical determinism. As we move beyond the realm of absolute predictability into the domains of probabilities, thermodynamics, and quantum uncertainties, Laplace's demon stands as a stark contrast and a reminder of a deterministic ideal that science once heralded. A beautiful, if elusive, horizon that has shaped centuries of thinking about the universe's ultimate nature. As the 19th century dawned, the deterministic edifice constructed during the Enlightenment faced new and profound challenges that would gradually erode the notion of absolute predictability epitomized by Laplace's demon. Two transformative developments, thermodynamics and the study of chaotic systems, ushered in the rise of probabilities, fundamentally changing how scientists and philosophers understood the behavior of the natural world and the limits of determinism. Thermodynamics emerged from efforts to understand heat, energy, and the behavior of gases that often appeared erratic and unpredictable. Classical Newtonian mechanics could describe the trajectories of planets or billiard balls with breathtaking precision, but it struggled with the disorder and randomness that seemed inherent in the microscopic world of molecules and atoms. Early thermodynamicists like Rudolf Clausius, William Thomson, Lord Kelvin, and James Clerk Maxwell observed that gases' properties, such as pressure and temperature, could be described reliably in statistical terms, rather than precise movements of individual particles. Maxwell's famous kinetic theory modeled gases as vast swarms of molecules in constant, rapid motion, colliding unpredictably. Pioneering physicist Ludwig Boltzmann attempted to reconcile the molecular chaos with deterministic Newtonian physics by introducing statistical mechanics. While individual particles followed deterministic laws, the overwhelming complexity and number of particles provided only probabilistic descriptions of the system's overall behavior. Boltzmann's formulation conveyed that from the disorderly motions emerges order on average, embodied in quantities like entropy, a measure of the system's disorder or the number of microscopic configurations consistent with its macroscopic state. This insight introduced a crucial new idea. Even within a fundamentally deterministic framework, practical predictability was limited to probabilities rather than certainties. The second law of thermodynamics, stating that entropy tends to increase in an isolated system, added an arrow of time, a directionality to physical processes, which was deeply at odds with the time-reversible laws of classical mechanics. Where Newtonian equations were symmetric in time, macroscopic phenomena showed irreversibility, eroding the notion that the universe's future could be perfectly predicted from its present. Alongside thermodynamics, the late 19th and early 20th centuries witnessed the emergence of chaos theory. This field studies deterministic systems that behave in highly sensitive and seemingly unpredictable ways, a phenomenon captured in the phrase sensitive dependence on initial conditions. Even infinitesimally small differences in starting states can lead to wildly divergent outcomes over time, a hallmark of chaotic behavior. Edward Lorenz's pioneering work in weather modeling during the 1960s famously revealed how minor variations in decimal places could cause drastically different weather predictions, a phenomenon now called the butterfly effect. This sensitive dependence shattered the illusion of practical determinism. Although governed by deterministic differential equations, chaotic systems resist long-term precise prediction because perfect knowledge of initial conditions is impossible. Chaos theory melds the notions of determinism and unpredictability. The systems it describes adhere strictly to deterministic laws, yet their complexity ensures that their future states can only be forecast with limited precision. This subtle twist redefines the landscape. Determinism remains true in principle, but the capacity to utilize it for prediction is fundamentally constrained. Together, thermodynamics and chaos theory illustrate how probabilities naturally arise in physical theory. Unlike Laplace's deterministic universe, where precise knowledge guarantees perfect prediction, these advances reveal a world where the effective description of systems relies on statistics, chance, and approximation. Philosophically, this rise of probabilistic thinking resituates the human relationship with nature's laws. It tempers the optimistic Enlightenment ideal of a fully knowable universe with humility regarding the complexity inherent in natural phenomena. Scientists must embrace uncertainty not necessarily as ignorance, but as an intrinsic feature of how complex systems function. Moreover, probabilities challenge the classic dichotomy between determinism and randomness. They suggest a layered reality where deterministic microscopic laws coexist with emergent unpredictability at macroscopic scales. This dual character profoundly impacts discussions about free will, since probabilistic causation introduces possibilities for non-strictly determined events. As we approach the 20th century, the rise of probabilities sets the stage for even deeper revolutions in our understanding of determinism. We will soon encounter the quantum realm's inherent uncertainties, where probabilities do not simply emerge from ignorance or complexity, but seem embedded at nature's core. For now, thermodynamics and chaos theory mark a key transition. They illuminate the nuances and limits of classical determinism, showing how predictability recedes in the face of vast complexity and probabilistic realities, thereby reshaping the ongoing dialogue about the universe's deterministic character and our place within it. As we continue our journey through the evolving understanding of determinism and the universe's intricate machinery, we arrive at one of the most thought-provoking theoretical paradoxes in physics: Maxwell's demon. Proposed by the brilliant 19th-century physicist James Clerk Maxwell, this thought experiment intertwines the realms of thermodynamics, information, and determinism, challenging our intuitive grasp of the second law of thermodynamics and unveiling profound questions about the role of information in physical reality. To appreciate Maxwell's contribution, we first must recall the second law of thermodynamics, which states that in an isolated system, entropy, a measure often associated with disorder, does not decrease over time. This law underpins the so-called arrow of time, an observed directionality from order toward increased disorder, and is foundational for the fields of physics, chemistry, and cosmology. The second law implies an irreversible process. Heat flows from hot bodies to cold, and systems evolve toward thermodynamic equilibrium, where no net energy gradients exist. Maxwell's demon imagines a microscopic, intelligent entity, informally dubbed the demon, capable of observing individual molecules in a gas-filled container divided into two parts. This demon can selectively open and close a tiny door between the two compartments, allowing only fast-moving, hot molecules to pass in one direction and slow-moving, cool molecules in the opposite direction. By doing so, it effectively concentrates heat in one portion of the box and reduces entropy, apparently violating the second law. At first glance, this thought experiment seems to provide a loophole, a way to decrease entropy without expending energy, thus challenging the fundamental assumption of irreversibility and the deterministic certainty associated with thermodynamic laws. The demon, acting through information processing, appears to reverse the natural, deterministic march toward equilibrium. However, deeper analysis over the following decades revealed that the paradox is resolvable when considering the physical nature of information. In the mid-20th century, physicists like Leo Szilard, Rolf Landauer, and Charles Bennett demonstrated that the demon's knowledge acquisition, memory storage, and especially the erasure of information incur thermodynamic costs. Landauer's principle, for instance, establishes that the erasure of a bit of information is a fundamentally irreversible process that increases entropy by at least a specific minimal amount. This insight elegantly preserves the second law. The demon cannot violate thermodynamics because its operations, observing, deciding, and forgetting, are physical processes subject to thermodynamic constraints. Information, far from being an abstract or purely mathematical notion, assumes a real physical presence intricately linked to energy and entropy. Maxwell's demon thus highlights the profound role information plays in the physical universe. It reveals that information isn't merely a description or bookkeeping device for physical states, but an active player influencing the evolution of systems. The processing and manipulation of information themselves constitute physical acts bound by the laws of thermodynamics. From a deterministic perspective, Maxwell's demon brings a nuanced complexity. Previously, determinism was often thought of simply in terms of mechanical processes and physical states evolving predictably under fixed laws. Yet here emerges the realization that the acquisition and handling of information embedded in physical systems also influence the system's behavior. The demon's manipulation of molecular motion is a function of its information processing, which itself obeys physical and thermodynamic laws. Thus, determinism extends beyond mere particle trajectories to encompass information dynamics. Moreover, the demon invites us to reflect on the subjective aspects of measurement and observation in physical processes. While the underlying molecular motions obey deterministic Newtonian mechanics, the demon's agency introduces a feedback loop where knowledge and physical action intertwine. This interplay becomes a precursor to more complex debates about observation and information in quantum mechanics. In broader terms, Maxwell's demon serves as a bridge between classical physical laws and the emerging recognition that information theory and computation are integral to understanding the universe. It propels a shift from viewing the universe purely as mechanical to seeing it as a system where information, entropy, and physical law coalesce. This thought experiment also touches on questions relevant to the limits of determinism. For example, if information handling is fundamentally physical and constrained, then no agent, no matter how powerful, can arbitrarily override natural laws. The physical embedding of information processing imposes conditions on control and predictability, moderating the scope of determinism's reach. Today, Maxwell's demon continues to inspire research in quantum information theory, thermodynamics, and the emerging science of computation, where energetic cost, entropy, and information remain deeply intertwined. It reminds us that understanding the universe's ultimate nature requires integrating not only particles and forces, but also the information that describes and shapes their evolution. As we move forward to explore how quantum mechanics further challenges classical determinism, the lessons of Maxwell's demon provide a vital conceptual foundation. They highlight that physical laws encompass more than just matter and motion. They include the dynamics of information, observation, and the fundamental constraints that prevent paradoxical violations of universal principles. This insight deepens and broadens our grasp of the complex, layered fabric from which reality is woven. As the 20th century unfolded, the sturdy edifice of classical physics, built upon centuries of mechanistic and deterministic thinking, encountered profound challenges from a groundbreaking scientific revolution: quantum mechanics. This revolutionary framework not only provided astonishing success in describing atomic and subatomic phenomena, but also shattered the long-standing assumption of certainty at the heart of the classical worldview. In doing so, it cast determinism into question and forced a fundamental re-examination of the nature of reality itself. Prior to the advent of quantum mechanics, the Newtonian conception of a clockwork universe reigned supreme. Scientists believed that, with sufficient information about initial conditions and the natural laws, the entire future and past could be predicted with arbitrary accuracy. However, as experimental techniques advanced and new phenomena emerged, such as blackbody radiation, the photoelectric effect, and atomic spectra, it became clear that classical physics could not account for nature's subtleties at the microscopic scale. Quantum mechanics emerged from these puzzles, beginning with Max Planck's introduction of energy quantization in 1900, followed by Albert Einstein's explanation of the photoelectric effect, Niels Bohr's atomic model, and the formulation of wave mechanics by Erwin Schrödinger and matrix mechanics by Werner Heisenberg. Collectively, these developments unveiled a reality at the smallest scales that defied intuitively deterministic explanations. Unlike classical particles, quantum entities display a wave-particle duality, sometimes behaving like discrete particles, at other times showing interference patterns characteristic of waves. This duality suggested that the classical picture of particles following precise trajectories was insufficient. Instead, quantum systems are described by a mathematical object called the wave function, a probability amplitude that encodes the likelihood of finding a particle in various states or locations. Crucially, quantum mechanics introduces inherent uncertainty. Heisenberg's famous uncertainty principle formalizes the idea that certain pairs of physical properties, such as position and momentum, cannot be simultaneously known with arbitrary precision. This limitation is not due to technological shortcomings or ignorance, but reflects a fundamental property of nature. Probabilities lie at the core of quantum descriptions. When scientists perform measurements on quantum systems, they cannot predict definite outcomes in all cases. Rather, they predict probabilities for possible outcomes. This probabilistic nature revolutionized the conception of causality and determinism, suggesting that even with complete knowledge of a system's wave function, only statistical predictions are possible. Moreover, the act of measurement itself plays a perplexing role. Upon measurement, a quantum system's wave function appears to collapse into a definite state, but this collapse process is not described deterministically by the standard quantum formalism. Instead, it introduces an element of randomness or indeterminacy, further undermining classical certainty. The Copenhagen interpretation, developed chiefly by Niels Bohr and Werner Heisenberg, embraced this probabilistic framework and regarded the wave function as a tool for predicting measurement outcomes rather than a direct representation of objective reality. According to this view, nature at the quantum level is fundamentally indeterminate, and the very notion of definite properties prior to measurement is abandoned. These implications sparked intense debate among physicists and philosophers. While some, like John von Neumann, accepted the indeterministic formalism as fundamental, others, most notably Albert Einstein, found it deeply unsatisfactory. Einstein famously remarked, "God does not play dice," expressing his conviction that the quantum description was incomplete and that an underlying deterministic theory must yet exist. Experimental advancements, such as the famous double-slit experiment and subsequent tests of Bell's inequalities, have supported the non-classical, probabilistic predictions of quantum mechanics, making it one of the most experimentally successful theories in science. Yet, the philosophical implications remain profound and unsettled. Quantum mechanics, therefore, shattered classical certainty by revealing a universe where unpredictability is woven into the fabric of reality, where causality is governed not by deterministic trajectories, but by probabilistic amplitudes and measurement-induced collapses. It heralded a new chapter in the story of determinism, one characterized by both unprecedented predictive power and fundamental mysteries. As we proceed to explore interpretations like the Copenhagen view, many worlds, and hidden variable theories, as well as the deeper questions about entanglement and the role of observation, it becomes clear that quantum mechanics not only revolutionized physics, but also reshaped our understanding of fate, chance, and the possible limits of determinism in the universe. Following the revolutionary emergence of quantum mechanics and its shattering of the classical deterministic worldview, the Copenhagen interpretation crystallized as one of the first and most influential attempts to make sense of the profound, often perplexing nature of the quantum world. Developed primarily through the collaborative efforts of Niels Bohr and Werner Heisenberg in the 1920s and 30s, the Copenhagen interpretation embraces the probabilistic heart of quantum mechanics and posits a radical shift in how reality is to be understood at the microscopic scale. At its core, the Copenhagen interpretation asserts that the quantum wave function does not describe a concrete physical reality in the classical sense, but instead encodes our knowledge or information about potential outcomes. Rather than representing an electron or photon as having definite properties at all times, the wave function provides a mathematical tool to compute probabilities of various measurement results. This paradigm abandons the classical ideal that physical systems possess well-defined attributes independent of observation. Instead, quantum properties like position, momentum, spin, and energy exist not as definite values, but as probability distributions, a superposition of possibilities, until measured. The act of measurement forces the system into one particular definite state in a process known as wave function collapse. This collapse is inherently probabilistic, governed by the Born rule, which gives the probability that each possible outcome will be realized. Before measurement, all outcomes coexist as possibilities. After measurement, reality chooses a definite state, but in a fundamentally unpredictable manner, in contrast to deterministic classical laws. The Copenhagen interpretation also introduces the principle of complementarity, championed by Bohr. Complementarity holds that quantum entities exhibit dual, mutually exclusive characteristics, such as wave-like interference and particle-like localization, that cannot be observed or defined simultaneously. To fully understand quantum phenomena, one must accept that multiple classical descriptions, which contradict each other in a classical framework, together capture the richness of quantum reality. Another crucial aspect is the strict distinction between the quantum system and the classical measurement apparatus. The measuring device, described in classical terms, interacts with the quantum system, resulting in the observed definite outcome. This cut, or boundary, reflects the interpretation's pragmatic approach. Quantum mechanics predicts measurement outcomes accurately, but does not delve into the ontological status of the wave function beyond its role as a tool for prediction. Philosophically, the Copenhagen interpretation embraces an epistemic stance, viewing quantum probabilities as statements about our knowledge, what can be known, rather than ontological statements about intrinsic randomness in nature. However, it leaves open the ontological question of what really exists before measurement, often described as a shift from an objective reality to a reality contingent on observation. While this interpretation achieved remarkable predictive success and remains widely taught and used, it also generated vigorous debate and criticism. Some viewed the inherent randomness and observer dependence as a fundamental break from classical realism, even unsettling or incomplete. The infamous debates between Einstein and Bohr highlighted sharply divergent views, with Einstein asserting that God does not play dice, seeking a deterministic underpinning beyond the Copenhagen framework, while Bohr defended the probabilistic complementarity-based understanding as the best reflection of empirical reality. Moreover, the notion of wave function collapse and the special role of measurement introduced conceptual difficulties, such as the measurement problem. What exactly constitutes a measurement, and how does the collapse process occur? These puzzles have spurred alternative interpretations and extensive philosophical exploration. In summary, the Copenhagen interpretation places probabilities at the very core of physical reality, as described by quantum mechanics. It boldly revises the classical notions of determinism and objective reality, replacing them with a worldview where certainty is fundamentally limited and observation shapes the phenomenon observed. This shift challenges us to rethink deeply held assumptions about causality, reality, and knowledge. As we move forward, exploring other interpretations like the many worlds or hidden variables, as well as investigations into entanglement and non-locality, it is crucial to appreciate how the Copenhagen interpretation remains a cornerstone, a profound, if imperfect, map of the quantum domain's probabilistic essence, documenting a monumental transformation in our understanding of the universe's fundamental fabric. Continuing the exploration of quantum mechanics and its implications for determinism, we arrive at one of the most fascinating and mathematically elegant interpretations: the many worlds interpretation, often associated with physicist Hugh Everett III, who proposed it in the late 1950s. This interpretation offers a radically different perspective on quantum phenomena, one that strives to restore a form of determinism at the quantum level by reimagining how reality itself unfolds. At its heart, the many worlds interpretation challenges the Copenhagen view's reliance on wave function collapse as an inherently probabilistic, indeterministic process triggered by measurement. Instead, it posits that the wave function, which encodes all possible quantum states, never collapses. Instead, the universe's wave function evolves deterministically, governed entirely by the linear and unitary Schrödinger equation. According to this view, all possible outcomes of quantum measurements actually occur, but in separate branching worlds or universes. When an observer measures a quantum system, the combined system plus observer evolves into a superposition of states, each representing a different outcome, and the universe effectively splits into distinct branches for each possibility. Each branch evolves independently, and observers within each world perceive a single definite outcome, unaware of the other branches. This bold proposal dispenses with the randomness and indeterminacy characteristic of the Copenhagen interpretation, replacing it with a deterministic multiverse where every conceivable outcome is realized somewhere. Uncertainty and probabilities emerge from subjective ignorance, An observer finds themselves in one branch but cannot access the others, thus experiencing outcomes probabilistically, even though the universal wave function's evolution is strictly deterministic. One of the remarkable aspects of the many worlds interpretation is its mathematical parsimony. It adheres strictly to the fundamental quantum formalism without adding ad hoc collapse postulates or special roles for measurements. Everything in the universe, including observers and their measuring devices, is quantum and evolves according to the same unitary laws. However, this deterministic multiplicity of realities is deeply counterintuitive. It compels us to envision not a single unfolding history, but a vast branching cosmology where reality splits incessantly, producing a staggering number of parallel worlds. This has profound philosophical implications about identity, the nature of reality, and our place within a constantly dividing cosmos. Critics of many worlds raise questions about the interpretation's ontological extravagance, the proliferation of countless unseen universes, and about how to rigorously recover the standard quantum probabilities and the born rule within this framework. Nonetheless, ongoing work in decoherence theory helps explain how distinct worlds become effectively independent and why observers perceive definite outcomes, lending credence to the approach. Importantly for our discussion of determinism, the many worlds interpretation offers a clear affirmation of quantum determinism. The universal wave function's evolution is unitary and fully deterministic, leaving no fundamental role for chance. The appearance of randomness reflects the observer's subjective uncertainty about which branch they inhabit, not any fundamental indeterminacy in physical law. This reinvigorates deterministic perspectives by extending them into the quantum domain, suggesting that the universe's ultimate foundation may be a grand, deterministic structure of branching realities. It reframes probabilistic events as emergent from the complex architecture of the wave function, rather than intrinsic randomness. The many worlds interpretation also intertwines intriguingly with cosmological and philosophical questions, potentially explaining quantum phenomena at cosmic scales and challenging traditional conceptions of causality, identity, and free will. As we continue, we will explore contrasting views that strive to preserve determinism or introduce hidden variables, as well as experiments testing the very foundations of quantum theory. But for now, many worlds stands as a towering example of how the quest for determinism in the universe has evolved, displaying its enduring vitality and capacity to inspire radical reimaginations of reality itself. As we delve deeper into the mysteries of quantum mechanics and the challenges it poses to determinism, it is essential to consider one of the most significant critiques and counterproposals in the history of quantum theory: the notion of hidden variables, championed by none other than Albert Einstein. Alongside this idea, the landmark Einstein-Podolsky-Rosen (EPR) paradox sharpened the debate about the completeness of quantum mechanics and the possibility of an underlying deterministic reality. Einstein, deeply uneasy with the inherently probabilistic nature of quantum mechanics espoused by the Copenhagen interpretation, famously expressed his discomfort with the idea that fundamental processes might be intrinsically random. He asserted that God does not play dice, underscoring his belief that the universe's behavior must be governed by deterministic laws, even if we lack full knowledge of them. To reconcile quantum theory with this conviction, Einstein and his collaborators Boris Podolsky and Nathan Rosen formulated a thought experiment in 1935, now known as the EPR paradox, that sought to demonstrate that quantum mechanics, as commonly understood, was incomplete. The EPR paradox involves a pair of quantum particles prepared in an entangled state, a condition wherein the properties of one particle are intrinsically correlated with those of the other, no matter the spatial distance separating them. According to quantum mechanics, measuring an observable, like the spin, on one particle instantly determines the corresponding property of the other particle, seemingly violating the principle of locality, that no information can travel faster than the speed of light, and challenging the deterministic, local picture of reality. Einstein and his colleagues argued that this spooky action at a distance suggested that quantum mechanics was a statistical theory lacking a deeper underlying layer of hidden variables. These hypothesized variables would deterministically specify the properties of particles, preserving both locality and causality. In other words, quantum mechanics' probabilistic predictions would emerge from ignorance about these hidden variables, analogous to how classical statistical mechanics emerges from averaging over unseen microscopic details. This proposal set the stage for an intense and long-lasting debate about the nature of reality, locality, and determinism. The idea of hidden variables promised to restore a deterministic and local framework beneath quantum phenomena, offering a more classical intuition of the universe. However, the conceptual landscape grew more complex with John Bell's theoretical work in the 1960s. Bell formulated inequalities, mathematical relations that any local hidden variable theory must satisfy. Subsequent experiments, beginning with those of Alain Aspect and others in the 1980s, and continuing to the present day, have demonstrated violations of Bell's inequalities, strongly suggesting that local hidden variable theories cannot reproduce all the predictions of quantum mechanics. These results imply that any hidden variable theory consistent with experiment must abandon locality, allowing for non-local correlations between entangled particles. Such theories replace locality with a different kind of determinism that permits instantaneous influences across space, underscoring a more subtle and less intuitive kind of determinism than the classical ideal. One notable example of a non-local hidden variables theory is the de Broglie-Bohm pilot wave theory. This interpretation restores determinism by positing that particles have precise positions guided by a pilot wave, evolving deterministically, but it incorporates explicit non-local connections, allowing instantaneous interactions across distances. The EPR paradox and hidden variables question forcefully emphasize that the deterministic nature of physical reality cannot be taken for granted, especially when quantum phenomena are involved. They compel us to reconsider classical assumptions about locality, causality, and completeness in our understanding of nature. More broadly, these investigations reveal the richness and subtlety of quantum mechanics, where determinism may survive, but only informs vastly different from classical expectations. The quest to reconcile quantum phenomena with deterministic principles remains one of the most profound challenges in physics, carrying deep philosophical and foundational significance. As we proceed to explore experimental tests of these ideas, such as Bell's theorem experiments and the nature of quantum entanglement, it becomes evident that the question of determinism in the quantum realm is far from settled. Instead, it opens windows onto an enriched conception of reality, one where the notions of determinism, locality, and randomness intertwine in ways that continue to intrigue and challenge modern science. In the quest to unravel the profound mysteries at the heart of quantum theory, Bell's theorem stands as a monumental milestone that meaningfully intersects with the deeply rooted question of determinism. Formulated by the Northern Irish physicist John Stuart Bell in 1964, this theorem provides a concrete way to test the compatibility between the principles of locality, that no influence can travel faster than light, and the concept of hidden variables, often invoked to restore determinism to quantum mechanics. Bell's theorem does not merely contribute to physics, it sharply challenges our most fundamental assumptions about how nature operates. To understand Bell's theorem, we must recall the backdrop against which it emerged. Earlier, Einstein, Podolsky, and Rosen, the EPR paradox, argued that quantum mechanics was incomplete, implying that hidden variables might underlie the apparent randomness and non-local influences in entangled quantum states. Hidden variable theories aimed to restore a deterministic and local reality, wherein outcomes are precisely determined by unknown parameters, preserving the classical notions of causality and separability. What Bell accomplished was brilliant and revolutionary. He derived inequalities, now known as Bell inequalities, that any local hidden variable theory must satisfy when predicting correlations between entangled particles measured at distant locations. These inequalities served as a litmus test, a sharp theoretical tool to differentiate quantum mechanical predictions from those of deterministic local hidden variable models. Quantum mechanics, however, predicts violations of Bell inequalities due to the entangled nature of quantum states. Measurements performed on one particle instantaneously influence the state of its partner, regardless of the distance separating them, leading to correlations stronger than those allowed by any local classical theory. What makes Bell's results so striking is that it converts what was once a philosophical dispute into an empirically testable question. Starting in the 1970s, and especially after seminal experiments by Alain Aspect and his collaborators in the 1980s, numerous experiments have systematically violated Bell inequalities. These empirical results have been replicated with increasing sophistication and loophole-free designs, overwhelmingly supporting the quantum mechanical predictions and ruling out a vast class of local deterministic hidden variable theories. The implications are profound and multifaceted. Firstly, these experiments show that the universe cannot be both local and deterministic in the classical sense. At least one of these cherished principles must be abandoned. Second, they affirm the inherently non-local character of quantum entanglement, where spatially separated particles exhibit correlations that seemingly defy relativistic constraints on signaling. This outcome reshapes our conceptions of causality and determinism. Either we accept non-local hidden variables, like those proposed in Bohmian mechanics, or embrace intrinsic indeterminism as fundamental, consistent with the standard interpretation of quantum mechanics. Bell's theorem, therefore, does not disprove determinism entirely, but circumscribes its plausible forms in the quantum realm. Determinism may survive as a non-local phenomenon, but classical local determinism, the kind resting on a neatly causal and separable reality, is untenable. Philosophically, Bell's work reinvigorates debates about realism, locality, and causation, confronting us with counterintuitive facets of nature, where the whole becomes irreducibly more than the sum of its parts. It forces a reconsideration of the notions of information transfer, coordination, and the deep structure of reality. Today, Bell's theorem remains a foundational pillar in discussions about the nature of reality, quantum foundations, and even emerging fields like quantum information and quantum computing. It exemplifies how precise theoretical reasoning allied with ingenious experimentation can probe the limits of our understanding, revealing unexpected truths about whether and how the universe conforms to deterministic laws. As we continue, upcoming discussions on quantum entanglement, the double-slit experiment, and cosmic implications will build upon these insights. Bell's theorem serves as a compass, guiding us through the perplexing terrain where determinism, randomness, and quantum reality intersect in challenging and inspiring ways. Quantum entanglement stands as one of the most intriguing and mystifying phenomena encountered within modern physics, profoundly shaping our understanding of determinism and the deep interconnections woven into the fabric of reality. At its essence, entanglement refers to a quantum state in which two or more particles become so intimately linked that the state of each particle cannot be fully described independently of the others, regardless of the spatial distance separating them. This phenomenon challenges classical intuitions about locality, causality, and even the nature of information itself. The story of entanglement is intimately tied to the early debates in quantum mechanics, notably emerging as a key element in the Einstein-Podolsky-Rosen (EPR) paradox. As discussed previously, Einstein and his colleagues highlighted how measurements on one particle of an entangled pair instantaneously determine the state of its partner, even if they are light years apart, seemingly defying the speed limit imposed by relativity. This spooky action at a distance was Einstein's term, reflecting both fascination and unease. From a purely mathematical standpoint, entangled states are described by joint wave functions that cannot be factored into separate, independent parts. Unlike classical correlations, which arise from prior interactions and shared histories, quantum entanglement exhibits correlations that are fundamentally stronger and do not admit local explanations. The results of measuring entangled particles show patterns that violate classical Bell inequalities, testifying to the genuine quantum nature of these connections. Quantum entanglement implies that the informational content relating entangled particles transcends classical concepts of space and time. Once particles are entangled, their properties are linked in a holistic manner. A measurement on one particle instantaneously influences the joint state, updating what we predict about the other particle, despite no apparent signal traversing the intervening distance. This challenges the classical causality embedded in a local, realist worldview. Experimental confirmation of entanglement's predictions has been one of the triumphs of physics over the last several decades. Advances in quantum optics and communication technologies have made it possible to entangle photons, electrons, and even larger, more complex systems, verifying that entangled correlations persist over increasing distances. These experiments have not only confirmed quantum mechanics' counterintuitive predictions, but also opened the door to practical applications like quantum cryptography and quantum computing. Philosophically, entanglement forces a reevaluation of the concept of information within physics. Unlike classical information, which presumes independent, localized carriers, quantum information embodied in entangled states is inherently non-local and cannot be decomposed into parts. This poses profound questions about the nature of reality and the limits of classical descriptions. Entanglement also plays a pivotal role in debates about determinism. While the evolution of the overall quantum state is governed deterministically by the Schrödinger equation, measurements produce outcomes that appear fundamentally probabilistic. The instantaneous correlations between entangled particles demonstrate that deterministic evolution can coexist with non-local correlations defying classical intuitions. Furthermore, entanglement challenges traditional notions of separability, the idea that distant systems possess independent realities, and prompts alternative perspectives where entangled systems are fundamentally indivisible wholes. This intertwining of parts in a non-classical unity suggests a universe more interconnected at a fundamental level than classical mechanics envisioned. Modern quantum information theory builds extensively upon entanglement, quantifying and exploiting it for technologies, including quantum teleportation, entanglement swapping, and quantum networks. These advances underscore entanglement's status not just as a philosophical curiosity, but as a tangible resource shaping future technology. As our exploration advances toward the double-slit experiment and the role of observation in quantum mechanics, entanglement's foundational importance serves as a backdrop, reminding us that the universe's deep structure challenges our intuitive concepts of space, causality, and determinism, compelling us to embrace a more nuanced and interconnected picture of reality. The double-slit experiment stands as one of the most profound and elegant demonstrations of quantum mechanics' enigmatic nature, illuminating deep questions about observation, reality, and determinism. Its history and implications have fascinated scientists and philosophers alike for over 2 centuries, and it continues to serve as a powerful touchstone in understanding the interplay between measurement and the fundamental behavior of matter. Initially conceived in the early 19th century by Thomas Young to demonstrate the wave nature of light, the classical double-slit experiment showed that light passing through 2 closely spaced narrow slits creates an interference pattern on a screen behind them, alternating bright and dark bands characteristic of wave phenomena. This phenomenon contradicted the then-dominant particle theory of light, establishing a wave-particle duality that would become central to modern physics. With the advent of quantum mechanics in the 20th century, the double-slit experiment assumed an even deeper significance. When single particles, such as electrons or photons, are sent one at a time through the 2 slits, an interference pattern still gradually emerges on a detector screen, as if each particle simultaneously passes through both slits and interferes with itself. This astonishing result defies classical intuitions about particles as localized, distinct entities, and reveals the fundamentally probabilistic and wave-like behavior of quantum objects. However, the plot thickens when which-path information, the knowledge of through which slit the particle actually passes, is sought. If an observer attempts to detect or measure the particle at either slit, the interference pattern disappears, replaced by a pattern consistent with classical particles passing through one slit or the other. In other words, the act of observation irrevocably alters the system's behavior, collapsing the superposed wave function into a definite particle-like path. This phenomenon vividly encapsulates the quantum measurement problem, the paradoxical relationship between the deterministic evolution of the wave function, according to Schrödinger's equation, and the apparent randomness and collapse introduced by observation. The observer effect highlighted by the double-slit experiment suggests that reality at the quantum scale is intertwined with acts of measurement, forcing us to confront whether physical properties have meaning independent of observation. Philosophically, the double-slit experiment challenges classical determinism. If a particle's behavior depends on whether it is observed and exhibits fundamentally probabilistic outcomes, then the clear-cut chain of cause and effect presumed by classical physics is disrupted. The experiment tantalizes us with the possibility that reality itself is not fixed, but contingent upon interactions with measuring devices or observers. Further explorations and variations of the experiment, including delayed choice and quantum eraser setups, add subtlety by demonstrating that decisions to observe or erase which path information can be made after the particle has passed through the slits, yet still influence the interference outcome. Such results suggest the non-classical temporality and contextuality of quantum events, where cause and effect interplay in counterintuitive ways. Moreover, the double-slit experiment connects intricately with the concept of wave function superposition, reinforcing how quantum systems exist in multiple potential states simultaneously until observed. This phenomenon defies classical realism, where objects have definite properties at every moment, and invites interpretations ranging from the Copenhagen interpretation's observer-dependent collapse to the many worlds branching universes. In addition to philosophical intrigue, the experiment has spurred numerous technological and scientific developments. It underlies the principles of quantum coherence, interference, and entanglement, essential ingredients in quantum computing, cryptography, and advanced microscopy. In sum, the double-slit experiment serves as a crystalline illustration of how observation fundamentally shapes quantum reality. It compels us to rethink notions of determinism and the nature of existence, highlighting that at the quantum level, reality resists simple description and is intimately linked with the very act of measurement or observation. As we progress to examine cosmic scales and how determinism operates in the vast universe, the lessons from the double-slit experiment remain vital reminders of the subtle dance between knowledge, observation, and the unfolding fabric of reality. As our journey into the nature of determinism broadens from the microscopic quantum realm to the vast expanse of the cosmos, we encounter compelling questions about how determinism operates on a cosmic scale, particularly regarding the universe's initial conditions and their profound influence on its entire evolution. The interplay between determinism and cosmology compels us to reflect on whether the large-scale unfolding of the universe is predetermined by these initial conditions and the fundamental laws of physics, or if intrinsic contingencies and limitations arise. Modern cosmology, largely founded on Einstein's theory of general relativity, describes the universe as a dynamic space-time fabric shaped by matter and energy. The dominant model, the Big Bang theory, posits that the universe began approximately 13.8 billion years ago from an extremely hot, dense, and highly ordered state. This initial state can be viewed metaphorically as the cosmic seed from which all subsequent structure and complexity have blossomed. At first glance, this scenario suggests a strongly deterministic framework. The general relativistic equations, combined with initial conditions specifying the distribution of matter, energy, and curvature, determine the universe's subsequent expansion, the formation of galaxies, stars, planetary systems, and ultimately everything, including life itself. If one possessed perfect knowledge of these initial conditions and the governing physical laws, it seems, in principle, possible to predict the entire cosmic history. However, the devil lies in the details of what exactly constitutes these initial conditions and the scope of our understanding and predictive capacity. The conditions at or near the Big Bang involve energies and densities so extreme that our current laws of physics, including general relativity and quantum mechanics, strain under such regimes. Not yet having a complete and unified quantum theory of gravity, physicists recognize that the initial singularity, representing the Big Bang's earliest moment, is a boundary where conventional physics breaks down. This uncertainty invites questions about determinism's status in the very genesis of the universe. Is the universe's birth a singular event uniquely fixed by prior causes? Or does it admit an ensemble of possibilities? Theoretical constructs like quantum cosmology and the application of quantum principles to the entire universe suggest that the initial state could exhibit probabilistic features, potentially undermining classical deterministic narratives. Furthermore, cosmic inflation, a brief epoch of rapid exponential expansion in the universe's infancy, introduces its own nuanced implications. Inflationary cosmology, proposed by Alan Guth and others, accounts for the observed large-scale homogeneity, isotropy, and flatness of the universe, while providing a mechanism for generating tiny quantum fluctuations that seed the formation of galaxies and cosmic structures. These quantum fluctuations, inherently probabilistic, mark an essential source of cosmic indeterminism embedded at the universe's beginning, subtly blurring the line between determinism and chance at the largest scale. Another key element influencing cosmic determinism is the concept of causal horizons. Due to the finite speed of light and the universe's expansion, regions of spacetime can be causally disconnected. No signal or influence from one region can reach the other within the universe's lifetime. This segmentation limits the scope of deterministic causality. Beyond our observable universe lies a vast expanse potentially governed by different initial conditions or even physical laws, inaccessible to direct observation and prediction. Cosmologists also explore cyclic or multiverse models in which our universe is one among many, each with differing initial conditions and physical parameters. If true, this renders the uniqueness of our universe's initial state and its deterministic power more complicated. What we observe is but one branch within a larger ensemble, with broader implications for the meaning and limits of determinism on cosmic scales. Moreover, the flow of time and entropy at cosmic scales intertwine with determinism. The second law of thermodynamics and the arrow of time arise prominently at cosmic dimensions, linked closely to the universe's initial low entropy state. This foundational low entropy beginning is itself a profound mystery and essential to the development of complexity and life, hinting at finely tuned initial conditions with profound causal ramifications. Philosophically, contemplating determinism in cosmology transforms the question from the predictability of isolated events to the origins and conditions underpinning existence and the very structure of reality. It challenges us to consider not only how the universe evolves, but why it has the particular initial parameters permitting the laws and structures we observe. In sum, determinism on the cosmic scale is a complex interplay between fixed physical laws, the universe's initial conditions, and quantum and potentially probabilistic elements emerging from the earliest moment of existence. While classical physics might suggest a rigidly predetermined cosmos, modern theoretical and observational advances reveal a more intricate and nuanced picture, where determinism coexists with profound questions and open horizons. As our exploration progresses into cosmological models and beyond, this reflection on cosmic determinism grounds our inquiry in the grandest context imaginable, reminding us that the question of the universe's determinism remains as vast and mysterious as the cosmos itself. The vast expanse of the cosmos invites us to explore not only its wondrous grandeur, but also the profound questions about the universe's origin, evolution, and ultimate fate, including the degree to which determinism governs its unfolding. In this chapter, we delve into the cosmological models that have shaped our understanding of the universe's earliest moments and its large-scale structure, focusing particularly on the Big Bang, the theory of cosmic inflation, and the concept of causal horizons. These developments deepen and challenge our reflections on determinism at the cosmic scale. The Big Bang model describes the universe as expanding from an extremely hot, dense, and compact initial state around 13.8 billion years ago. Observations of the cosmic microwave background radiation, CMB, the glow of relic radiation permeating space, and the redshift of distant galaxies lend strong empirical support to this framework. The Big Bang implies that the entire cosmos has been evolving dynamically, governed by the laws of general relativity and particle physics. Within classical general relativity, the Big Bang is associated with an initial singularity, a point of infinite density and curvature where known physical laws break down. This singularity represents a conceptual limit rather than a physical reality we can fully describe, compelling physicists to consider quantum gravitational effects that might smooth or replace this initial state. To resolve some of the conceptual and observational puzzles arising from the Big Bang theory, such as the horizon problem, flatness problem, and monopole problem, the theory of cosmic inflation was introduced in the early 1980s by Alan Guth, Andre Linde, and others. Inflation posits a brief epoch of extraordinarily rapid exponential expansion in the universe's infancy, occurring just fractions of a second after the Big Bang. During inflation, tiny quantum fluctuations were stretched to macroscopic scales, seeding the inhomogeneities responsible for the distribution of matter and formation of galaxies we observe today. This blending of quantum effects with cosmic-scale dynamics illustrates a remarkable interplay between chance and determinism. The underlying equations governing inflation are deterministic, yet the initial quantum fluctuations introduce an irreducible probabilistic element that affects structure formation. Following inflation, the universe continues expanding, but at a more tempered pace consistent with observational data. Yet inflation's imprint, minute variations in temperature and density, remains etched in the cosmic microwave background, providing a detailed snapshot that cosmologists analyze with exquisite precision. Another essential concept in cosmology tied to determinism is that of causal horizons. Due to the finite speed of light and the dynamic evolution of spacetime, causal horizons delineate the regions of the universe that can influence or be influenced by us. Events beyond our particle horizon cannot affect us because signals from them have not had time to arrive since the Big Bang. These horizons impose limits on what can be known, observed, or predicted from our vantage point in the universe. They contribute to an inherent cosmic censorship of information, fragmenting the cosmos into causally disconnected patches. This segmentation raises important questions about determinism. Even if physical laws are universal and deterministic, are there fundamental epistemic limits on our predictions due to these horizons? Can events beyond our horizon influence or restrict the determinism we experience locally? Moreover, speculative notions like the multiverse and eternal inflation suggest a cosmos far grander than our observable universe, with potentially different physical parameters and initial conditions realized in separate bubble universes. In such scenarios, determinism at the global scale becomes a more subtle concept, as our observable universe is but one instantiation amid countless others, a view that challenges classical ideas of a singular deterministic cosmic history. Altogether, the Big Bang, inflationary theory, and causal horizons weave a complex tapestry intertwining determinism and indeterminism, observation and mystery. The deterministic laws describing space-time and matter frame the universe's evolution, yet quantum fluctuations and horizon-induced informational limits introduce irreducible elements of chance and uncertainty. This interplay enriches our understanding of cosmic determinism, underscoring that while the laws governing the universe's large-scale behavior are robust and predictive, the initial conditions and quantum seeds carry a probabilistic signature that resonates through cosmic history. As we continue exploring concepts such as the flow of time, entropy, and the arrow of time, these cosmological insights ground our reflections firmly in the universe's grandest scale, revealing the intricate balance between determinism and the open questions that remain as boundless as the cosmos itself. Time's arrow, the unmistakable one-way flow from past to future, is a hallmark of our everyday experience. Yet, when we turn to the fundamental physical laws that govern the microscopic world, we find an intriguing paradox. Most of these laws, whether Newtonian mechanics, electromagnetism, or even quantum mechanics, are time-symmetric, meaning they allow processes to run equally well forward or backward in time. This stark contrast between the reversible equations at the microscopic level and the irreversible phenomena we observe at macroscopic scales presents a profound puzzle central to understanding determinism, causality, and the nature of reality. Central to the explanation of this irreversibility is the concept of entropy, introduced by the pioneering work of Rudolf Clausius, Ludwig Boltzmann, and others in the 19th century. Entropy, a measure of disorder or the number of microscopic configurations corresponding to a macroscopic state, tends inexorably to increase in isolated systems, a principle encapsulated in the second law of thermodynamics. This law reflects an asymmetry. While the fundamental equations do not distinguish time's direction, the behavior of large ensembles of particles does, relentlessly progressing from orderly to disordered states. Boltzmann's statistical interpretation of thermodynamics bridges microscopic reversibility and macroscopic irreversibility. He showed that although individual molecules obey reversible laws, the overwhelmingly larger likelihood of systems transitioning toward states with higher entropy gives rise to a practical arrow of time. The universe's journey, starting from an extraordinarily low entropy state at the Big Bang, unfolds as entropy increases, dictating the thermodynamic arrow pointing from past to future. Importantly, this leads to a nuanced view of determinism. The microscopic laws remain deterministic and reversible in principle, but the macroscopic world exhibits effective irreversibility and the practical impossibility of perfectly retracing individual particle trajectories. This means that while the future is determined by the present, the past can be obscured in the mists of high entropy and loss of information about precise initial conditions. Reversibility and entropy also intersect intriguingly with emergent phenomena and complexity. For instance, in chaotic systems, tiny differences in initial conditions amplify exponentially, making long-term predictions practically impossible despite the underlying deterministic laws. This complexity introduces effective irreversibility and unpredictability, enriching the tapestry of time's arrow and determinism. Beyond thermodynamics, other arrows of time exist. The cosmological arrow aligns with the universe's expansion direction. The radiative arrow describes the preference of electromagnetic waves to diverge rather than converge, and the psychological arrow reflects our perception of time flowing only forward. These arrows interrelate, yet pose further questions about their origins and linkage. Philosophically, the flow of time challenges straightforward deterministic pictures. It forces us to confront why time seems to have a privileged direction, why causes precede effects, and how this connects with the fundamental laws. Some interpretations suggest that the asymmetry of boundary conditions, particularly the universe's initial low entropy state, grounds the arrow of time, implying that determinism includes constraints from these cosmic starting points. Furthermore, considerations from quantum mechanics add depth. Quantum decoherence explains how superpositions effectively collapse into classical mixtures due to environment-induced interactions, embedding irreversibility within the quantum realm and linking measurement and observation to time's arrow. In summary, time's arrow is a remarkable confluence of reversible deterministic laws and emergent irreversible phenomena. This duality shapes our very understanding of causality, prediction, and the flow of events, reminding us that determinism does not exist in isolation, but is embedded within a rich temporal landscape that shapes the unfolding fabric of the universe. As we further explore free will, consciousness, and the fabric of reality, the enigma of time's arrow remains central to unraveling how determinism and the lived experience of time coalesce in our universe. The age-old tension between determinism and free will reaches a critical nexus when viewed through the lens of neuroscience and contemporary philosophy. If the universe operates fundamentally according to physical laws, as physics suggests, what room remains for human freedom? This question, once purely philosophical, now finds itself at the crossroads of empirical investigation and metaphysical reflection. From a neuroscientific perspective, the human brain is a complex physical system, governed by biochemical and electrical processes that, in principle, obey the laws of physics and chemistry. Advances in brain imaging and experimental psychology have made glimpses into the mechanisms of decision-making increasingly precise. Experiments, such as those conducted by Benjamin Libet and successors, reveal that neural activity signaling choices arises milliseconds before subjects feel a conscious intent to act. This temporal precedence of unconscious brain processes has profound implications, suggesting that what we perceive as free will might, at least in some cases, be a post hoc rationalization of decisions already initiated by deterministic brain states. Neuroscience raises fundamental questions. Are our thoughts and choices the inevitable consequence of prior physical states? Are we merely complex machines executing causal chains beyond conscious control? If so, then free will, understood as the ability to have genuinely acted otherwise, might be an illusion, yet the philosophical debate remains robust and multifaceted. A central distinction emerges between metaphysical free will, freedom as non-deterministic agency, and compatibilist notions where free will is reinterpreted as freedom compatible with deterministic causation. Compatibilists argue that freedom pertains to acting according to one's desires and rational deliberations, even if those desires themselves have deterministic causes. Thus, moral responsibility and meaningful choice can coexist with a deterministic universe. Conversely, incompatibilists maintain that determinism and free will cannot coexist. If our actions are predetermined, genuine freedom does not exist. Some incompatibilists subscribe to libertarian free will, positing non-deterministic causes, or indeterminism, as essential for authentic agency, though how indeterminism supports control remains debated. Recent perspectives also examine the role of consciousness and self-reflection in free will. Conscious deliberation may be seen not as the initiator of all choices, but as a higher-order process capable of monitoring, inhibiting, or endorsing impulses generated at subconscious levels, thus providing a functional freedom within physical constraints. Moreover, concepts from quantum mechanics have spurred discussions about whether fundamental indeterminacies at the quantum level might offer a physical basis for free will. While some propose that quantum randomness could inject genuine unpredictability into brain processes, critics caution that randomness alone does not equate to meaningful freedom or control. Philosophers and scientists continue to explore how complex neural architectures might yield emergent properties, including intentionality and agency, that transcend simple deterministic descriptions. This emergentist view holds that while neurons obey physical laws, the collective dynamics produce novel phenomena attributable to higher-level systems. Ultimately, the question of free will in a physical universe remains open-ended, challenging both our scientific understanding of the brain and our philosophical interpretations of choice, agency, and responsibility. It urges humility and curiosity, reminding us that the phenomena of consciousness and freedom lie at the deepest intersections of physics, biology, and philosophy, areas where definitive answers continue to elude us, but where exploration reshapes our understanding of what it means to be human. The debate over whether determinism and free will can coexist is a central and enduring concern in philosophy, known as the conflict between compatibilism and incompatibilism. This issue transcends pure metaphysics, directly impacting ethics, law, and our understanding of personal responsibility. To fully grasp this divide, we need to explore what each position entails and how they conceptualize the relationship between causality and human freedom. Incompatibilism holds that free will and determinism are fundamentally at odds. Under determinism, every event, including human decisions, is the inevitable outcome of preceding causes governed by universal laws. If this is true, the argument goes, then our sense of freedom, the ability to have acted otherwise, is illusory. This position suggests that if our actions were predetermined, moral responsibility becomes problematic because agents lack genuine control over their choices. Libertarianism, a prominent form of incompatibilism, insists on the reality of free will as a non-determined agency. Libertarians posit that for true freedom to exist, some actions must be undetermined by prior states of the universe. They require an element of indeterminacy, or spontaneity. However, introducing indeterminism raises further philosophical puzzles. If actions arise by chance, how does that confer responsibility? This tension highlights the complexity of defending libertarian free will. Compatibilism, by contrast, argues that determinism does not negate free will. Rather, it redefines freedom in a way consistent with causal determinism. Compatibilists maintain that freedom is not about the randomness of choice, but about acting according to one's desires, intentions, and rational deliberations without external coercion. From this perspective, a person can be free and responsible even if their decisions flow from prior causes, so long as they align with their internal motivations. For example, David Hume, an early compatibilist, emphasized that liberty is the power to act or not act according to the will, meaning that if one's actions are voluntary and not externally compelled, they are free. Contemporary philosophers like Daniel Dennett have expanded this view, suggesting that freedom and responsibility emerge naturally within complex, causally determined systems like human brains. The compatibilist approach resolves many practical and ethical concerns by preserving responsibility and agency without requiring metaphysical libertarian freedom. It situates free will as a higher-order capacity grounded in rationality, self-control, and the alignment of motives. Nonetheless, critics of compatibilism argue that redefining freedom so that it is compatible with determinism dilutes its traditional meaning. They claim that if our preferences and desires are themselves determined, then true alternative possibilities do not exist, a notion that threatens the moral weight we assign to our choices. Furthermore, recent findings in neuroscience and quantum physics complicate the debate. Neuroscience's challenges to the timing of conscious intent and quantum indeterminacy introduce empirical tensions that both compatibilists and incompatibilists must account for. Yet most would agree that these empirical insights do not settle the philosophical dispute, but rather enrich the conversation. Another nuanced position is semi-compatibilism, which maintains that moral responsibility can be sustained regardless of whether determinism is true or false, a stance that separates the metaphysical question of free will from the normative question of responsibility. Ultimately, the compatibilism versus incompatibilism debate reflects deep differences in how freedom is conceptualized and how determinism is interpreted. It reveals the subtle interplay between metaphysical principles and lived human experience, showing that notions of choice, causality, and agency are woven tightly into the fabric of philosophy, science, and daily life. As this debate continues, it informs not only the philosophy of freedom, but also shapes how we assess justice, ethics, and personal meaning in a universe that may or may not be fundamentally deterministic. It highlights that questions about determinism inevitably lead us to examine the very essence of what it means to act as autonomous agents in a complex, interconnected world. The world around us presents a fascinating paradox when it comes to understanding determinism and randomness through the lens of complex systems. On one hand, classical physics paints a world governed by fixed laws and predictability, while on the other, nature displays a bewildering array of phenomena marked by apparent randomness and unpredictability. The study of chaos theory and complex systems bridges this divide, revealing how deterministic systems can exhibit behavior that appears random and how complexity itself emerges from simple rules. Chaos theory emerged as a formal area of study in the mid-20th century, notably through the work of meteorologist Edward Lorenz, who discovered that small changes in initial conditions of weather models led to vastly different outcomes. This sensitivity to initial conditions popularly described as the butterfly effect, means that even in perfectly deterministic systems, where future states follow inexorably from present ones, long-term prediction becomes practically impossible due to tiny uncertainties growing exponentially. Such systems show deterministic chaos. They obey strict laws, yet their behavior appears irregular, complex, and unpredictable to observers. This duality complicates our classical notion of determinism. Theoretically, every state follows causally from its predecessors, but due to limits in measurement precision and computational capacity, the practical predictability ceases after certain timescales. The universe, or many subsystems within it, straddle the line between order and disorder, predictable and chaotic. Beyond physics, complex systems pervade natural and social sciences, from fluid turbulence and population dynamics to economic markets and neural networks. These systems often display emergent properties that cannot be straightforwardly deduced from their parts, challenging reductionist views. They demonstrate self-organization, feedback loops, and non-linear interactions leading to rich, adaptive, and unpredictable patterns. Randomness in complex systems arises from intrinsic non-linearities and interdependencies. Where previously statistical methods merely represented ignorance about initial states, now randomness itself can be a fundamental component of system behavior. Yet this randomness is distinct from quantum indeterminacy. Rather than fundamental unpredictability, it emerges from intricate deterministic processes complicated by the sheer number of interacting components. Philosophically, this realization reshapes the concept of determinism from rigid predictability to a subtler idea encompassing both precise laws and inherent unpredictability rooted in complexity. It suggests that randomness and order are entwined, with chaos acting as a bridge, blurring clear-cut divisions between determinism and chance. This nuanced picture also has implications for free will and agency, as living organisms, including humans, operate within and emerge from complex systems exhibiting chaos and randomness, creating possibilities for emergent behavior not easily reducible to simple deterministic chains. In summary, randomness and chaos expose a richer, layered nature of determinism in the natural world. They reveal that even deterministic laws can give rise to unpredictability and novelty, compelling us to rethink the meaning of chance and causality in a universe marked by complexity and interconnection. This understanding broadens the scientific and philosophical landscape, preparing us to consider even more radical ideas about the universe, including simulation theory and quantum information concepts explored in the following sections. Simulation theory, a provocative and increasingly discussed idea at the intersection of philosophy, computer science, and cosmology, posits that our entire universe, including ourselves and everything we observe, might be a sophisticated simulation, a programmed reality generated by computational processes beyond our current understanding. This concept raises profound questions about determinism by suggesting that the universe's behavior could be predetermined or algorithmically controlled, challenging conventional notions of physical law and free will. The roots of simulation theory can be traced to philosophical skepticism about reality itself, echoing ancient questions about illusion and appearance. However, in its modern incarnation, it draws heavily upon the explosive growth of computational technology and digital simulation, alongside explorations into the computational foundations of physics. In 2003, philosopher Nick Bostrom famously formalized the simulation argument, suggesting that one of the following propositions is likely true: that intelligent civilizations do not reach a stage capable of running detailed ancestor simulations, that they choose not to run such simulations, or that we very probably live within such a simulation. While this argument does not prove we live in a simulation, it compellingly frames the possibility as scientifically and philosophically relevant. If the universe is a simulation, determinism could be understood in new terms. Instead of natural laws arising from fundamental physical constants and interactions, these laws might be the operational rules encoded in the underlying computational program. Consequently, the universe's entire history, from cosmic evolution to the flutter of a butterfly's wings, would unfold according to a program's algorithmic instructions. This computational determinism implies a form of predetermination. The outcome of any event is, in principle, set by the simulation's initial program and its processing algorithm. Yet, an important nuance lies in whether the simulation incorporates randomness internally or permits user or observer interactions that might influence outcomes. Some hypothetical simulators might embed quantum-like randomness or adaptive processes, preserving a form of indeterminacy within the programmed reality. Technological advances in artificial intelligence and virtual reality have made simulation theory culturally salient, as creators simulate increasingly lifelike and complex virtual worlds. The possibility that an advanced civilization could create a simulation indistinguishable from base reality challenges our assumptions about the nature of existence. Philosophically, simulation theory raises questions about knowledge and epistemology. If all experiences and observations exist within a simulated environment, can we ever empirically verify or falsify it? Does this render our scientific laws provisional or emergent from deeper computational frameworks? Moreover, it touches on issues of consciousness. Are simulated beings truly conscious? And what does that imply for free will and agency within such a universe? Critics point out challenges to the theory, including the enormous computational resources required even for simulating a small portion of the universe, and the problem of infinite regress. If our universe is a simulation, what about the reality of the simulators themselves? From the perspective of determinism, simulation theory offers a radical reframing. It suggests that what we perceive as natural law and randomness might ultimately be artifacts of computational programming and processing constraints. This opens up possibilities for controlled manipulation, reprogramming, or emergent phenomena beyond the original program. In the broader discussion of determinism, simulation theory invites us to reconsider the assumptions about fundamental reality. It inspires awe and philosophical humility, reminding us that our conception of the universe may itself be limited by the software running beneath the surface. As we proceed to explore quantum computing, information theory, and the role of observers, simulation theory acts as a conceptual bridge, a nexus where physics, technology, and philosophy converge, challenging us to rethink the nature of reality, determinism, and human existence itself. The emergence of quantum computing marks a profound juncture in our understanding of both computation and the fundamental nature of reality itself. As classical computers manipulate bits of information, ones and zeros, to perform calculations, quantum computers harness the principles of quantum mechanics, such as superposition and entanglement, enabling entirely new modes of computation. This technological revolution prompts a deep and intriguing question: is reality itself computable? In other words, can the universe, with all its complexity and nuance, be fully described by computational processes? To explore this, we first need to understand that the universe, according to quantum mechanics, operates on information. At the quantum level, information is not just abstract data. It is embedded in the state of particles and fields, influencing how they evolve and interact. Quantum information theory treats this information as physical and fundamental, leading to the insight that processing and transferring quantum information lies at the core of the universe's behavior. Quantum computing leverages qubits, quantum bits, that differ from classical bits by existing in superpositions of states. This enables quantum computers to perform certain computations exponentially faster than classical counterparts, such as factoring large numbers or simulating complex quantum systems. Because the universe itself is a quantum system, quantum computers hold promise for simulating physical phenomena directly, offering insights that classical machines cannot efficiently provide. The idea of the universe as a vast quantum computer was notably suggested by physicist John Archibald Wheeler, who coined the phrase "it from bit," proposing that all physical things arise from underlying information processes. This perspective aligns with digital physics and computational universe theories, which propose that the fabric of reality emerges from discrete information processing, similar to how computers operate. Computability theory asks, can all physical processes be simulated algorithmically? If the universe is computable, then, in principle, a sufficiently advanced quantum computer, or another form of universal computational device, could emulate any physical system to arbitrary precision. This vision corresponds elegantly to classical deterministic frameworks and complements quantum indeterminacy by embedding probabilities and uncertainties within computable algorithms. However, the question is far from settled. Some aspects of quantum theory, like quantum randomness and non-local correlations, challenge traditional notions of algorithmic computability. Moreover, phenomena in quantum gravity involving spacetime at Planck scales may involve structures or dynamics beyond standard computational frameworks. Several researchers have proposed that the universe might be a kind of quantum automaton, processing information at the most fundamental level. This view facilitates conceptualizing phenomena from black hole thermodynamics to quantum entanglement as computational processes, inviting a unified informational approach to physics. On the other hand, some scholars argue that intrinsic unpredictability or fundamental physical processes might elude computation, hinting at limits to what can be algorithmically simulated. This poses profound philosophical questions about the nature of physical law and the scope of scientific explanation. In addition, the interplay of observers in quantum mechanics, where measurement affects reality, suggests that computation may not be purely objective, but intertwined with information acquisition and consciousness, expanding the boundaries of what computability encompasses. In conclusion, quantum computing and information theory have revolutionized our understanding of computation and fundamentally altered how we contemplate reality's structure. While the hypothesis that reality is computable remains speculative, it opens fertile terrain bridging physics, computer science, and philosophy. The exploration of computability in physics challenges us to rethink the universe not just as a collection of particles and forces, but as a dynamic processor of information, blurring the lines between physical law, computation, and the very essence of existence. As we move forward, these ideas will continue to shape cutting-edge research into quantum gravity, multiverse theories, and the role of consciousness in physics, highlighting computation as a central thread in the ongoing unfolding narrative of determinism and our quest to understand the universe. As we continue unraveling the intricate tapestry of determinism, quantum mechanics, and the structure of reality, we arrive at a profound and often enigmatic concept: the role of observers in shaping reality. At its intersection with consciousness and measurement, this theme probes not only the physical mechanics of the universe, but also the nature of experience itself, raising questions about whether and how observers participate in constructing the reality they observe. The pivotal recognition that observation plays a fundamental role in quantum mechanics stems largely from the measurement problem. Quantum systems exist in superpositions, simultaneous blends of all possible states. until an observation or measurement collapses this superposed wave function into a definite outcome. But what qualifies as an observation remains deeply contentious. Is it a mere physical interaction, or does it require a conscious observer to effectuate this collapse? The philosophical ramifications are immense. Early interpretations, like the Copenhagen view, often implied a special, perhaps even mystical, role for observers, placing consciousness at the heart of the transition from quantum possibilities to classical actualities. This observer-dependent reality challenges traditional objectivist frameworks that regard the universe as existing independently of measurement or perception. Various formulations have arisen to account for the observer's role. Some maintain a strict physicalist position. The measurement process involves the entanglement of the observed system with a measuring apparatus, and decoherence processes effectively suppress quantum superpositions without invoking consciousness. In this light, observers are complex physical systems, and collapse is a practical phenomenon rather than a fundamental one. Others, however, explore interpretational frameworks like the Wigner's friend scenario, where consciousness indeed has a unique ontological status in determining outcomes. This view delves into the notion that conscious experience is not just passively receiving information, but actively participates in defining reality. Furthermore, such perspectives dovetail with panpsychist or idealist philosophies, proposing that consciousness is fundamental rather than emergent. This intimate connection between observers and reality construction resonates in theories where the fabric of space and time, or even physical laws, emerge from informational or computational substrates intertwined with observational acts. In this context, reality becomes participatory, with conscious agents and their measurements entwined in a cosmic dialogue. Neuroscience and cognitive science also weigh in, illuminating the brain's role in interpreting sensory data to produce the unified experience we call reality. The brain's construction of perceptual reality suggests that what we call objective is filtered, processed, and sometimes even created by the mind, blending empirical input with internal models and expectations. These insights challenge the naive realism once taken for granted, suggesting that reality as experienced is an active construction, not merely a passive window. The observer shapes and is shaped by reality, blurring the line between subject and object. From the perspective of determinism, if the observer participates in defining the physical state of the system, then the classical chain of cause and effect is subtly transformed. The act of observation might be more than a mere causal link. It becomes a fundamental aspect of reality's unfolding, introducing nuanced layers to determinism, where conscious choice and perception influence what manifests. While these ideas remain topics of ongoing research and philosophical debate, they reaffirm that understanding the role of observers is crucial to grasping reality's deepest nature. Whether viewing observers as complex machines, conscious agents, or fundamental participants, it becomes clear that consciousness and observation play indispensable roles in shaping the universe we inhabit. As we move forward to explore contemporary frontiers in quantum gravity and multiverse theories, the participatory nature of observation provides a compelling conceptual bridge, inviting us to reconsider the very foundations of physics and the profound enigma of our own existence within the cosmos. As we traverse the evolving landscape of physics and philosophy, we arrive at the cutting edge of inquiry, where the nature of determinism confronts the profound mysteries of quantum gravity and multiverse theories. Current frontiers in these fields blend profound theoretical insights, experimental aspirations, and deep philosophical challenges, collectively pushing our understanding of the universe's fundamental workings to its limits. Quantum gravity seeks to reconcile the apparently discordant pillars of modern physics: quantum mechanics, which governs the subatomic world with probabilities and indeterminacy, and general relativity, which describes the deterministic and geometrically elegant fabric of space-time and gravitation. The union of these frameworks is essential to describe phenomena occurring at the Planck scale, where the smallest lengths and highest energies prevail, such as inside black holes or at the universe's birth. Among the leading approaches to quantum gravity is string theory, which posits that the fundamental constituents of reality are not point particles, but tiny, vibrating one-dimensional strings whose modes of vibration give rise to known particles and forces. Within string theory, spacetime can emerge from more fundamental entities in higher dimensional frameworks. The theory suggests a vast landscape of possible vacuum states, potentially giving rise to a multiverse, an ensemble of universes each with different physical constants and laws. This picture raises profound questions about determinism. Within each universe, laws may remain deterministic, but the ensemble introduces a cosmic plurality that complicates straightforward causal predictability beyond our own cosmological domain. Loop quantum gravity is another influential framework that attempts to quantize spacetime itself, modeling it as a discrete, granular structure woven from quantum threads. This approach replaces the smooth continuum of classical spacetime with a quantized geometry, raising novel questions about time, causality, and the deterministic evolution of geometry under quantum rules. Both these approaches and their variants grapple with the nature of time, whether it is fundamental or emergent, and how to reconcile quantum uncertainty with classical determinism on cosmic scales. Some suggest that at the deepest level, determinism may be preserved in the evolution of a quantum gravitational wave function encompassing all possible cosmic configurations, reminiscent of the many worlds view extended cosmologically. Multiverse theories, spanning eternal inflation, string landscape, and quantum many worlds, depict a reality far richer than previously imagined, consisting of vast ensembles of causally disconnected regions or entirely separate universes. The notion of determinism within this sprawling ensemble is subtle. While each branch or universe may unfold deterministically according to local laws, the selection of which branch we inhabit involves quantum branching or global statistical distributions, presenting new layers of subtlety and philosophical debate. The holographic principle and developments inspired by black hole physics also reshape our conceptions of information and determinism. The idea that all information within a volume can be encoded on its boundary challenges classical intuitions and hints that information conservation is central to fundamental physics, possibly safeguarding determinism in unexpected ways despite apparent quantum ambiguities. Experimental verification of quantum gravity remains elusive, but astronomers, particle physicists, and quantum information scientists collaborate to probe phenomena that might reveal quantum spacetime effects or multiverse signatures. As theoretical models advance, they increasingly integrate information theory, quantum entanglement, and geometry, indicating that determinism may intertwine deeply with information processing at the universe's most fundamental level. Philosophically, these cutting-edge inquiries urge us to re-evaluate assumptions about causality, reality, and the meaning of laws in a landscape potentially composed of multiple realities or emergent spacetime. Determinism transforms from a simple, absolute rule into a complex tapestry woven from probabilistic quantum foundations, emergent classical realms, and a multiversal expanse. Current frontiers thus represent an exciting, open, and dynamic domain where physics meets metaphysics. They invite humility and curiosity, reminding us that while significant progress has illuminated many aspects of deterministic structure, The deepest nature of causality and reality remains one of humanity's grandest, tantalizing mysteries waiting to be unraveled. As we reach the culmination of our exploration into the question, is the universe deterministic? We find ourselves standing at the crossroads of centuries of inquiry, where physics, philosophy, and metaphysics intersect in profound and sometimes perplexing ways. Throughout this vast journey, from the ancient seeds of philosophical speculation to the latest frontiers of quantum gravity and information theory, we have witnessed a tapestry woven with threads of certainty, randomness, causality, and deep mystery. Initially, the human quest for understanding was rooted in the desire to find order, a cosmic architecture built upon unchanging laws and predictable motions. The ancient philosophers laid foundational concepts about cause and effect, necessity and contingency, planting the intellectual seeds that would flourish during the Enlightenment with the advent of Newtonian mechanics. Here, determinism crystallized into a powerful, elegant vision. The universe as a celestial machine, entirely predictable in principle given enough knowledge. Yet, as science advanced, cracks appeared in the deterministic facade. Thermodynamics introduced the inevitability of irreversibility and entropy's inexorable march, while chaos theory revealed the profound limits of prediction amidst complexity. Then, quantum mechanics shattered classical certainty, placing probabilities and observer-dependent realities at the universe's core. Interpretations such as Copenhagen challenged us to embrace indeterminacy, while many worlds and hidden variable theories offered determinism reimagined or restored in novel ways. The remarkable experiments testing Bell's theorem and probing entanglement defied classical intuitions about locality, causality, and realism. On cosmic scales, models of the Big Bang, inflation, and causal horizons revealed a universe whose initial conditions set the stage, but whose full narrative involves emergent complexities, quantum fluctuations, and potentially vast multiverses. Time's arrow and entropy anchored an asymmetric flow in a fundamentally time-symmetric world, bridging micro and macro realms. Philosophically, the tension between free will and determinism remains vibrant. Neuroscience points to mechanisms that challenge simple notions of agency, while compatibilism and incompatibilism offer competing yet compelling frameworks to understand freedom within or despite physical causality. The advent of computational paradigms, simulation theory, and quantum information opens fresh vistas where reality might itself be viewed as informational processing, further blurring the lines between physical law, chance, and observer participation. Throughout, the role of the observer, consciousness, and information has emerged as an indispensable element in interpreting and perhaps constituting reality itself. This participatory nature of existence invites us to reconsider the traditional boundaries between subject and object, determinism and experience. In sum, the question of whether the universe is deterministic cannot be answered simply or conclusively with our current knowledge. Instead, it remains a dynamic inquiry, one that evolves with our scientific discoveries and philosophical insights. Determinism persists as a powerful concept with compelling theoretical and practical entailments, yet it coexists with fundamental uncertainties, emergent complexities, and interpretive ambiguities. This vibrant interplay highlights not only the limits of our understanding, but the richness of the universe itself. It invites humility and wonder, encouraging an ongoing dialogue across disciplines and perspectives, a quest not merely for definitive answers, but for deeper comprehension of reality's profound mystery. Where do we go from here? The future beckons with promises of new theories, technologies, and perhaps entirely new paradigms. Whether through advances in quantum gravity, enhanced understanding of consciousness, or unexpected empirical revelations, our journey into the nature of determinism continues, reflecting humanity's perennial aspiration to fathom the cosmos and our place within it. As we arrive at the final stretch of our extensive exploration into the nature of determinism and the universe, we find ourselves enveloped in a vast landscape of profound, often perplexing, unanswered questions. The journey from ancient philosophical musings to contemporary scientific frontiers has illuminated much, but it also reveals how deeply mysterious the universe remains, inviting further inquiry across multiple domains. One pivotal open question is the ultimate nature of determinism itself. Is the universe fundamentally deterministic, inherently indeterministic, or does it embody a more complex fusion of both paradigms? Quantum mechanics challenges classical determinism with its inherent probabilities, yet interpretations like many worlds and hidden variable theories suggest deterministic layers yet to be fully understood. What is the true ontological status of the wave function? Does objective reality possess definite states independently of observation? Or is reality inextricably tied to the act of measurement and consciousness? Further, the role of consciousness in the fabric of reality presents a deep enigma. Is consciousness a mere epiphenomenon emerging from deterministic physical processes, or does it possess causal efficacy that influences the unfolding of events at quantum or cosmological scales? Can advances in neuroscience, physics, and philosophy converge to illuminate the interplay between mind and the universe, potentially redefining the boundaries between observer and observed? The question of free will remains central and unresolved. How can human agency be reconciled with physical laws? Does emergent complexity within deterministic or probabilistic frameworks create genuine freedom? Or are our choices predetermined or shaped by fundamental indeterminacies? Philosophers and scientists continue to debate compatibilism, incompatibilism, and libertarianism, grappling with implications for moral responsibility and the lived human experience. On cosmological scales, the initial conditions of the universe, the nature of time's arrow, and the measure and interpretation of multiverse landscapes remain fertile fields for discovery and debate. Can we ever empirically access or meaningfully theorize about realms beyond our causal horizon? Does the universe's beginning encode constraints or possibilities that fix the course of everything that follows? Moreover, as quantum gravity research and quantum information theory evolve, they raise subtle questions about the computability of reality and the ultimate limits of prediction and knowledge. Is the universe a computational structure? If so, what are the rules of the program, and can they be extracted or understood? Alternatively, do fundamental limits of computation and measurement impose insurmountable barriers to complete knowledge? In the realm of complex systems, chaos, and emergent phenomena, the interaction between determinism, randomness, and novelty invites deeper scrutiny. How do systems transform simple, deterministic rules into unpredictable, creative dynamics that underpin biology, consciousness, and society? Experimentally, the quest continues to test the foundations, probing quantum entanglement and non-locality, searching for signatures of quantum gravity, testing the boundaries of the standard model, and investigating the nature of dark matter and dark energy. Each advance may remodel our understanding of determinism and causality in unforeseen ways. Beyond science, these questions resonate with human meaning, touching upon spirituality, ethics, and existence itself. How do our cosmological and physical insights illuminate or challenge our sense of purpose and place in the cosmos? What does it mean to live authentically in a universe potentially governed by necessity and chance? Ultimately, the journey of inquiry is ongoing, propelled by curiosity, creativity, and humility. The universe, a puzzle both dazzlingly intricate and stubbornly elusive, invites us to explore with open minds and receptive hearts. As we advance, interdisciplinary dialogue across physics, philosophy, neuroscience, mathematics, and beyond will be essential. Our path forward holds promise for transformative understanding, reshaping not only science, but our very conception of reality, freedom, and existence. While certainty remains beyond reach, the pursuit itself is a testament to the enduring human spirit, striving to illuminate the profound question, is the universe deterministic? And within that question lies the boundless horizon of discovery yet to unfold.